start. Here we go. Okay, so you got some practice with points, getting the feel for the polar plane. Oh, actually, let me clear the count. Let's take a look at Clara. So one thing I want to point out with Clara is does this problem have to do with polar coordinates? Does this problem have to do with polar coordinates? I have a yes. Does it have to do with polar coordinates? No, not at all. Okay, so it's about parametric functions. Now, what may be confusing or where you may get tripped up is that our parameter in this problem is an angle. And it is the standard trig angle. So you're working with this. You're looking at the ray that connects the center of the silo with the point where the rope is peeling off. And the parameter for your parameter function is this angle. This angle here between the positive x-axis and the ray to the point where the rope peels off. But you're going to write her position. You're going to write x as a function of theta and y as a function of theta. This is not polar coordinates. This is not polar coordinates. This is a parametric function. This is a parametric function where we're writing the coordinates. We're still in the xy plane. We're still in the xy plane. And we're writing coordinates x comma y, but our parameter, each of those x and y are a function of theta, where theta is what I've described there. Okay? What is polar coordinates? Okay, well, yeah, we do in polar coordinates. We represent any point in the plane, but we don't use x and y to do it, right? We're not using x and y to represent points in the plane. We use theta and then the distance from the pole, r. So this doesn't have anything to do with polar coordinates other than they both have to do with that angle, okay? Polar coordinates is about, instead of writing points as x and y, about writing points as r and theta. Theta determines the direction then of positive r. Theta determines the direction of positive r. Okay, so when you're working through the Clara project, make sure you're in parametric function mode, and then realizing that your parameter is this angle to the where the terminal side of the angle is the point pointing to where the rope peels off. Okay, so I wanted to just. Some students have gotten confused in the past because we were working on polar coordinates while you're working on this, and then you need to distinguish between the two. Any questions on that? Does it make sense? Good? Okay, so let's talk about polar coordinates, right? Polar coordinates. Again, we sweep an angle. Good, right there. Okay, what's polar coordinates? We sweep an angle theta from the positive x-axis counterclockwise. And then once we have a theta, that determines the direction of positive r, right? Positive r is now in that direction. So r equals 1 is here, r equals 2 is here, 3, 4. So positive can point in any direction. Positive r can point in any direction in the plane from the pole. That direction determined by our angle theta. Right? And so then where are negative angles of negative values of r? Well, theta determines the direction of positive r. negative r is going to be exactly pi rotation away, or exactly the opposite direction. So now this is how you would determine negative. This would be negative r for that same angle. So this point right here, we could say what? Negative 3 comma theta. This point here would be something like the one that's shown there. Would be something like 1.2 comma theta. Whatever theta is. Okay, is that point right there. And again, you should hopefully that's making sense after you practice with the web work. Okay, so our functions then in polar coordinates are like this. R as a function of theta. R equals, and so in this case, R equals 3 sine theta. So we want to make heads or tails with this function, right? So as theta changes, R changes, and it gives you a set of points. And then we want to find out what all the points, the graph of all those points, right? So and this is going to be a big part of this polar graphing, or the polar coordinates module here is being able to sketch polar curves. So we're going to spend all day today and at least half of Monday, and you're going to have lots of practice sketching polar curves. And so you really have to understand the polar plane really well. And so it's good to force you to do that. So we're going to do r equals 3 sine theta. And so the way that we're going to do this is, the first thing we're going to do is we're going to sketch that in rectangular coordinates. So we're going to investigate y equals sine x. Sorry, 3. Y equals 3 sine x. And so we're going to have to reach back into pre-calculus and know how to sketch these variations on trig functions. If you've forgotten, you're going to need to brush up. So could you sketch a couple periods of 3 sine x? So the basic formula for variations on sines: a sine b x minus c plus d, like that. So do you know what just the plain old sine curves looks like? And if you had a form like this with all these other values involved, a variation or a transformation of sine, could you sketch it? So this one, so what does d do? Let's just talk through it. What would d do to the sine curve? Okay, that's a vertical shift. It's going to move it up and down. So you can think of d as the location of the midline, right? D is where the midline is. Okay. So what's our midline for ours? 0. There's no plus d. There's no plus anything. So the midline is going to be 0, right? The midline is going to be 0. What about a? So we're going to multiply whatever the sign is. We're going to multiply it by a. And so what does that do to the y coordinates? Magnifies the y coordinates by a. So it's going to stretch. Anything positive is going to be times a up, and anything negative is going to be times a down, right? So it's going to be a vertical stretch. This is called the amplitude of the wave. The amplitude of the wave is the height from the midline, right? It's the height of the wave from the midline. What do we got? So we know our midline is 0, and we've got 3 sine x. So what's our amplitude? 3. So our maximum value of sine is going to be, or of this curve, 3, minimum, negative 3. So it's the midline is 0, and y values are going to fluctuate between negative 3 and 3. Okay, what about b? What does b have to do with here? Okay, So B has to do with the period. It's an adjustment to the period. What's the standard period of sine of x? For what interval of x do we get one full cycle? For what interval of x do we get one full cycle? 2 pi, right? So 2 pi is when we get one full cycle. And when we sketch these, we take one full cycle and we divide it up by 4. That's how we're going to do this. So if 2 pi is our one period or one full cycle, then we're going to divide up into 4 pieces, and that's going to allow us to help us with the sketch. So I'm going to draw 2 periods here. So that's 2 pi. And that's 4 pi. So we're going to sketch 2. So is B the new period? It's not the new period. So if we didn't have C, then it would be Bx. And we get a full cycle when Bx, or that argument of sine, reaches 2 pi. So that would be that x value that would give us the period. So therefore the period, or the x interval that gives us the period, is equal to 2 pi over b. 2 pi over b. Okay, we don't have to worry about that on this one though. But those are the 3 things. So we're not going to really see phase shifts on our sketches, but you'll have to know how to get a transformation of sine using a midline shift, an amplitude change, and possibly a period change, okay? All right, so for this one, 3 sine x, we know our max and our min are 3 and negative 3 because the amplitude, the midline's at 0, and then our period is 2 pi. That's the standard, that's the period for just the standard sine and standard cosine. So then the last thing is, what does sine do? It's the y-coordinate as we go around the unit circle. So that starts, does that start at the minimum, the midline, or the max? The y-coordinate. Do you remember? Starts at 0 at the midline. And then as we go around the circle, pi over 2, the y-coordinate is max, right? Max. Back to pi, y-coordinate is back to 0. Don't draw these as straight lines, right? This is concave down. This is a curve. This is cupped down. It's not straight lines. Okay. Then from pi to 3 pi over 2, the y-coordinate goes down to the minimum. And then back to 2 pi, we're back to the midline. Something like that. And then it's going to repeat again. From 2 pi to 4 pi, the whole thing repeats again. So what we're going to do is we're going to use that 3 sine x in rectangular coordinates to help us sketch polar coordinates. By looking at the graph and looking how. So this is really theta. This is theta, and this is r. So I wrote y and x, but we're just to emphasize that I'm putting it in rectangular coordinates. But thinking about it in polar, then our horizontal axis is theta in the polar plane, and the y-coordinate is r in the polar plane. So we're gonna look at this graph that we've sketched, and we're gonna see how theta and r change together, and then we're going to apply that into our knowledge of the polar plane. Okay, so what are we gonna look at first? So this is theta going from 0 to pi over 2. So as theta goes from 0 to pi over 2, this first quarter period here, what does the radius do? Increases from what to what? 0 to 3. Okay, so we have to imagine so watch what happens. So as theta increases, each time theta increases, r increases, such that it starts at 0 and ends at 3. Did you see it? So we have the point theta 0, 0 is here, and then we can think about for each increasing value of theta, I'm going to get a greater and greater value of r each time until it reaches 3. So can you see that? So watch as theta increases from 0 to pi over 2, r is increasing from 0 to 3. So you're going to have to be able to do this without the animation, right? So you're going to have to be able to do this without the animation. As theta increases from 0 to pi over 2, values of r increase from 0 to 3. Did you see it? Does it make sense? So what will that look like? So now we want to graph all the points, right? All the points. As theta increases from 0 to pi over 2, r increases from 0 to 3. All right, then we look at the next thing here. Any questions on that? Does it make sense? As theta now goes from pi over 2 to pi, as theta goes from pi over 2 to pi, what does r do? R goes from 3 back to 0, and you see we've got symmetry here, right? So the same way that it went up to 3, it's going to go back down to 0, right? The same way that it went from 0 to 3, it's going to go back to 0. So imagine our angle changing this way, and then each time the angle increases, r decreases, meaning we're moving closer to the pole, right? So for each time the angle changes, r is sliding back from 3 to 0. So let's just watch the points first. Here we go, watch the points. So you see r is decreasing as theta increases to pi. So starting at pi over 2 again, as the angle increases, r decreases back to 0. So looking at the whole thing then, we already did this part. R increasing out to 3 as the angle increases from 0 to pi over 2. And now as the angle goes to the second quadrant from pi over 2 to pi, r decreases back to 0. Okay, next part. So starting at pi. Starting at pi, going from pi to 3 pi over 2, what does r do? Decreases to -3. So in this whole third quadrant, as the angle goes from pi to 3 pi over 2, r is getting more and more negative. What do values of negative r mean in the third quadrant? So if my angle, say, is pointed this way, and I have a small negative value, where will that be? Back here. And now if my angle is this, I'm going to have a slightly larger negative angle, like here. And then if my angle is this way, negative r is a greater negative here. So what's going to happen? It's just going to retrace. It looks like it's retracing. So now we're going from 0 to -3 as the angle comes through this quadrant. So it's going to retrace what happened in the first quadrant. So you can watch the point. So notice the point is on the red line now. That's negative values of r as the angle goes from pi to 3 pi over 2. And then likewise, this last quadrant from 3 pi over 2 to 2 pi, r is going from -3 to 0. So it's also going to be, this is all negative values. So in the fourth quadrant, negative values, graph where? Second quadrant, starting at -3, which is up here. So 3 pi over 2, -3 is here. And then we're going to have, as the angle increases this way, r is going to become less negative. It's going to increase, become less negative to 0. So that's going to retrace as well. So you actually retrace this curve twice as sine does one full period. So this particular curve, all it takes is a half a period of sine to get it. So once we went from 0 to pi, we had the whole curve, and then just repeats after that. Sometimes it will take, whatever the period of this function is, will be the same as what it takes to get the whole graph. Sometimes 2 periods of this graph. That's why I drew 2 periods to start with. Because sometimes you need 2 full periods or more to get the entire polar graph. So there's no guarantee that a period of whatever equation you're starting with is going to be a period, or it's going to give you the full polar graph. Sometimes it's half a period like this one, sometimes it's the full period, sometimes it's 2 periods. Okay, so that was an easy one to start with. So, any guesses as to what this may be? Does it look like a circle? Do we know for sure it's a circle? It looks like it, but we don't know that for sure without mathematically proving it. Okay, so if it's a circle, then we ought to be able to show that mathematically. So let's do that. So we know that r is 3 sine theta. So we know what circles are like in Cartesian coordinates, rectangular coordinates. So can we change this equation into the corresponding equation of x and y? If we can do that, and then it turns out to be a circle, then we've shown that it's a circle. So can we need to get this in terms of x and y. So what do we know about changing, what is x equal to in polar coordinates? And what is y equal to in polar coordinates? X equals r cosine theta, okay? That's always true. That's always true. X is always r cosine theta, and y is r sine theta. So somehow we got to get x and y involved here. So let's look on the right-hand side. We've got 3 sine theta, and y is r sine theta. So it would sure be nice if what? If we had what on the right side? So we got 3 sine theta. What we really need is what? R sine theta. So it would sure be nice if we had what? An r. Well, we got an equation, so we can do that. We can finagle it, right? What if we had 3r sine theta? And what would that be equal to? Yeah, but we need to maintain the equality of our original equation. So it would be r squared, right? So by multiplying both sides by r, I just got myself y here on the right. It's equal to 3y. Do you see it? And then what about r squared? What's that? X squared plus y squared, right? Pythagorean theorem. R is the hypotenuse of the triangle made up by x and y. So r squared is always x squared plus y squared. So by multiplying both sides by r, we did ourselves a big favor here. We made it easy to get the equivalent equation in x and y. So this is equivalent to r equals 3 sine theta. So now, is this circle? Is this a circle? Okay, well, our standard form of circle is, over here, x minus a squared plus y minus b squared, remember from parametrics, equals r squared. So can I get this to look like that? What am I going to do first? Get all my y's together, all my x's together, so I'm going to subtract 3y. And what do I need? I need perfect squares, right? I need x minus a quantity squared, y minus b quantity squared. So the x minus a, that's good. That's x minus 0, right? That's x minus 0 quantity squared. What about this y squared minus 3y? I need that to be a perfect square binomial. So I have to complete the square. So how do we complete the square? You take half of this number right here, the coefficient of y, you take half of it and square it. And that completes the square. So what's half of that squared? 3 halves squared is 9/4. That's going to complete my square to get me this. I'm trying to get that. Okay. But if I add 9/4 on this side, I got to add 9/4 on this side. So then I got x squared plus y minus what squared? So if I've completed the square right, now this thing is a perfect square binomial. It's y minus something squared. What is that something? 3 halves. And then equals what squared? 3 halves squared. So we've got the circle. Center is 0, positive 3 halves. Radius is 3 halves. Is it that circle? So center, 0, 3 halves is 1 1/2. Radius, 3 halves. It's the circle we thought it was. Center at 0, 3 halves. Radius, 3 halves. Okay, so you'll have some questions like this, going back and forth between a polar equation and the corresponding Cartesian equation, x and y. So we sketched r equals 3 sine theta. We thought it might be a circle, and we just proved it. We just proved that it's the circle we thought it was. Center 0, 3 halves, radius 3 halves. Any questions on that? Okay, let's try. So let's talk about. So what about a line here? So let's say. How about this line? Does this seem? So this line with y-intercept 0, 0, 1, and rate of change -2. Does it seem fitting for polar coordinates? A line like that? Does it seem fitting for polar coordinates? Yeah, polar coordinates is really about like distance from the pole, right? So like the circle with center at the pole and radius 2 would be what? What's the equation of say this circle right here? No, in polar coordinates. So what's true about every point on that circle right there? R equals 2, right? R equals 2. It doesn't matter what the angle is, R equals 2. So circles kind of lend themselves well to polar coordinates because it's based on angles, right? Angles and distance from the pole. So that's kind of circles. But lines don't really, they're not really convenient in polar coordinates. So what is the equation of this line? Where are you? I didn't touch anything. I don't know why that just happened. The whole system. Oh. Okay, so this line has equation -2x plus 1. What would it be in polar coordinates? What would it be in polar coordinates? What does y equal? R sine theta. What does x equal? Cosine theta plus 1. So how would we find r as a function of theta? R as a function of theta, we need to solve for r. So we want to get all the r's on the left here. So r sine theta plus 2r cosine theta equals 1. Factor out r. So r is 1 over sine theta plus 2 cosine theta. That's kind of a weird equation, right? So it's like 1 over sine theta plus 2 cosine theta in the denominator. So this kind of agrees with the fact that, lines aren't convenient in polar coordinates. And so you don't get a convenient equation either. But still, you need to know how to go back and forth between, again, polar and Cartesian rectangular equations. Okay? So in polar coordinates, this is the equation of this line that I sketched, which is much more fitting to rectangular coordinates. That's why you get a nice, easy equation in rectangular coordinates and something kind of not very convenient in polar coordinates. Okay, any questions on that? Okay, so let's do another example of sketching. Have you try one. So let's try two cosine theta plus 2. So what are you going to do? First, you're going to sketch that in rectangular coordinates. Where theta, our polar angle theta, will be on the horizontal axis, and then the y-axis will be r. You're going to sketch that in rectangular coordinates. Again, 2 cosine theta plus 2. And then you're going to use your sketch to sketch it in the polar plane. You're going to look at intervals of theta. You're going to say, as theta increases from 0 to whatever, how does r change? And then you've got to imagine that in the polar plane. You're going to imagine that happening in the polar plane. And then you go to the next interval. As theta increases from this angle to this angle, what does r do? I don't think anyone's listening to me. Go ahead. What's that? Thank you. Everyone was just writing furiously. So if you want us to check your rectangular graph, that needs to be right before you can go on. So we'll come around and check to make sure you have that right. 2 cosine theta plus 2. This is no calculators. No calculators. Okay, so you ask yourself, as theta goes from 0 to pi over 2, what does r do? It goes from something to something. And then you have to imagine that angle increasing through that interval and r changing, right? R changing along that terminal ray as that changes. So as r goes from 0 to pi over 2, what does r do? Goes from what to what? So the graph, most of you got the graph, so it tells you as theta goes from 0 to pi over 2, r goes from 4 to 2. So that means at 0, we're going to start here at 4. That's why that point's there. As the angle rotates through this first quadrant, values of r are going to decrease until they reach 0, 2. So at the end, it's going to be at pi over 2, 2, or here, right? And r values are going to decrease. So here's what most students do. They just draw a straight line from there to there. But you got to think about r decreasing little by little as the angle increases. So a little bit less, a little bit less, a little bit less, a little bit less, something like this. As the angle changes from 0 to pi over 2, r decreases from 4 to 2. So yeah, so I think the big temptation is to come in like this. But if you're coming in like this, then what's r doing here? Is r decreasing or increasing? No, as the angle, if you draw your curve like this, then as the angle increases through here, what is r doing? It's increasing, but we want r to be decreasing the whole way. So when the angle's a little bit less than pi over 2, r's got to be greater, right? Not less. So don't draw like a line or like come in like this. R's got to keep decreasing the whole time. Make sense? So if you draw something like that, then you're saying r is increasing close to pi over 2. So let's show it. Here we go. Watch the points. As theta increases from 0 to pi over 2, r decreases the whole time. Then what? As we go from pi over 2 to pi, what does r do? Decreases to 0. So without the animation, you got to think to yourself, okay, the angle's going to rotate through here, and my r is going to keep getting less and less. And then until at pi, when I get to pi, then r is 0. Anybody have that before I put it up there? Before I went through it? This is what you got to get good at, okay? Next part. So now we're going from pi to 3 pi over 2. What does r do? Increases back to 2. So you got to imagine, you got to imagine that angle sweeping through the third quadrant, and r values every time theta increases a little bit, our point moves out. R is further from the pole. So this angle, r is out here. Then this angle, r is a little bit greater. Then this angle, r is a little bit greater. A little bit greater, a little bit greater, until we reach 2. So watch it. As the angle goes from pi to 3 pi over 2, the radius increases that whole time, out to 2. And then the last part, 3 pi over 2 to 2 pi, from 2 to 4, and it's going to mirror this, what this did. So imagine the angle sweeping through, r increasing the whole time. So here we needed exactly one period. Exactly one period of our original function gave us the whole graph. Sometimes it takes 2 periods. Okay, so this is called a cardioid, because it kind of looks like a heart. Okay, let's See if we can try one more. Any questions on this one? All right, why don't you try 3 sine of 2 theta. See how that goes. Okay, it's the same as the first one, but now the period is pi. Should get that the period is pi, not 2 pi. So we're going to get a full cycle of sine from 0 to pi instead of from 0 to 2 pi. So that's what that graph looks like. So our first thing then is from 0, not to pi over 2 anymore, but from 0 to what? So we're not talking about 0 to pi over 2 for this first little part. Now it's 0 to pi over 4, right? Because our period just got cut in half. So as we go from 0 to pi over 4, r goes from 0 to 3. So you could sketch the first and last point. So 0, 0, and then pi over 4, 3. And now we have to imagine the angle increasing through here. And as the angle increases, our r value increases. So it looks like this. As theta goes from 0 to pi over 4, r goes, oh, I was in the wrong spot. That was 4. From 0 to 3. And then as we go from pi over 4 to pi over 2, what does r do? Decreases back to 0, right? In the same way that it increased. So you can imagine, you can think symmetrically there. So now we're at pi over 2. As we go from pi over 2 to 3 pi over 4, what does r do? Decreases to, so here's 3 pi over 4, we're going to be at negative 3. Right here. So it's going to get more, as the angle turns through here, it's going to increase negatively in the fourth quadrant. So here's r going from 0 to negative 3 as the angle goes from pi over 2 to 3 pi over 4. and then back to 0 as we go to pi. So going 0 to pi gets you half of the graph, and if you keep going again, it's going to follow the same pattern. So positive r out to 3, back to 0, and then r goes from 0 to negative 3 and back to 0. And we get a 4-petal flower for that.